Hello, my name is Colin Crowley, and I will be presenting the paper ZOE Content-Based Anomaly Detection for Industrial Control Systems. Here is the agenda for the presentation. I'll first introduce the authors, then the paper. I'll go over the problem statement and scope. Section 4, Attack Detection and Proprietary Protocols, forms sort of the meat of the paper that explains the particular concept being presented. Section 5 goes into detail on the data sets that the authors used to test their detector. 6 evaluates the detector based on all of the input data sets and the different experiments that the authors performed. In Section 7, I'll cover the related work, and in Section 8, the conclusion. These are the authors of the paper. I won't butcher their names, but as you can see, they all come from the Institute of Systems Security at the University of Technology, Braunschweig. So this paper had a lot to do with proprietary binary protocols. Proprietary binary protocols are very prevalent in industrial control systems. However, content-based anomaly detection of proprietary protocols is difficult. So when we say content-based anomaly detection, we mean searching for anomalies among different internet traffic based on the content of the messages themselves. Obviously, that would be difficult if the protocols of the messages are proprietary. It's basically trying to search for an anomaly in messages in a language that isn't understood. So ZOE, which is the tool built by the authors, offers a new method of content-based anomaly detection. It derives what are called prototype models, which I'll go into further detail further in the presentation, that are specific to individual types of messages. And ZOE was designed for high entropy data, or data with high variance and noise. So this particular anomaly detection is difficult with data that is high entropy, and this is the particular problem that ZOE seeks out to rectify. So ZOE's contributions are the aforementioned prototype models for network messages, which characterize the structure and data of the messages. So even though the prototype isn't, or the protocol isn't understood, ZOE still attempts to build prototypes that characterize what it can see in the structure and content of the messages. And these are constructed in linear time, which is one of the key contributions that, that ZOE makes. ZOE is also noise resilient in its anomaly detection, which means that it is capable of pruning out irrelevant noisy features in the messages that are unnecessary for performing the anomaly detection. And so therefore, this is sort of how it's able to do robust anomaly detection for high entropy data, because it's able to sort of boil down the data to the most relevant features and the ones that, that characterize it the most, and also the ones that would be most likely to indicate an anomaly. And then after building their tool, they performed a large-scale evaluation using authentic SCADA data, 2 different industrial facilities, 5 entirely undocumented proprietary protocols that even the authors had no knowledge of the protocol, and 210 gigabytes of data. So taking a step back, we'll take a look at the exact nature of the problem that ZOE is setting out to solve. When it comes to anomaly detection in industrial control systems, there's a particularly high cost of error. That means that it is particularly important to reduce false negatives. And this makes sense because communication in an industrial control system are controlling physical processes. And so it's sort of necessary for messages to get where they're going, because otherwise the underlying physical processes might malfunction. There's also a lack of training data. Anomaly detection in general builds a model of normality. And so without sufficient amount of training data, it can be difficult to know exactly what is considered normal. And we also need examples of malicious data in order to test the detector to make sure that it actually does correctly flag malicious attacks as malicious. We have to keep in mind the semantic gap, which basically just means that anomaly detection does just that. It detects anomalies. It doesn't guarantee malice. So if something is flagged as anomalous, it's still necessary to have intervention or manual interpretation of that particular anomaly. And there's a large variability of input data, which, as I said before, is one of the particular problems with anomaly detection in ICSs and what ZOE is attempting to solve. Industrial networks are more homogeneous than general purpose networks, but aggregation and filtering of information is still essential. So now we move on to the particular way that ZOE does anomaly detection. So it first builds the prototype models. It partitions network traffic by similarity, constructing each prototype model as it goes. And then in order to perform noise resilient anomaly detection, it counts occurrences of features which arise as substrings of messages and disregards rare features using a frequency threshold. So these two sort of cornerstones of ZOE give some insight into how it's parameterized. We need to know how many number of message groups we want, so how many prototype models we want to create, and also what the frequency threshold is in order for thresholding disregarding rare features. And so, as we can see here, these are the two parameters that we need to provide in order to initialize an instance of ZOE. So this is how ZOE operates. This is how ZOE builds the prototype models. It constructs feature vectors by counting occurrences of substrings, aka features, in messages. And then samples are taken from the input data, and K clusters, K being one of the input parameters to ZOE, are initialized. So they're K clusters, aka K prototype models. And then subsequent messages are assigned to a cluster based on a proximity function. And so this is how ZOE is able to continue to construct the prototype models in linear time on the fly. There are two important memory optimizations that are employed. First, only counts of messages and their substrings are stored rather than the messages themselves. And also, ZOE makes use of the count, min, sketch data structures for probabilistic counting. The count, min, sketch data structure is similar to a Bloom filter, whereas a Bloom filter only tracks existence of an item in a set. It uses n booleans, and those booleans track just whether or not the item is in the set. Instead of booleans, the count, min, sketch data structure uses integers. And so for each of the hash functions that are computed based on the input, whatever those hash functions map to, those integers are incremented. And so an important note about the count, min, sketch data structure is that it may overestimate the counts of an item in the data structure, but it will never underestimate, which is sort of analogous to how a Bloom filter will sometimes give a false positive, but never a false negative. Noise resilient anomaly detection is the other cornerstone, aside from the prototype models, of what ZOE provides. So typical language models make noise reduction difficult in binary protocols due to the density, but the previously described prototype models are able to use the frequency information that I was just talking about that the count, min, sketch data structure store in order to prune irrelevant features. And so the two benefits that come from this application is that the size of the model is significantly reduced, saving space, and also the attacker's reach of play is reduced when attempting to mimic benign messages, which will come back whenever we talk about the evaluation. But it basically makes it more difficult for an attacker to mimic a benign message. So how does ZOE actually classify a message as malicious or as anomalous? It uses a scoring function to measure resemblance of a given message M with each of the K prototype models. In this setup, a low score indicates similarity, so the closer to 0, the more similar the message is with each of the K prototype models. And so ZOE takes the model capital M with the lowest score among each of the K models. So of all of the different prototype models, whichever one yields the lowest score is the one that it uses. And then the message is classified as malicious if it is above, and if that score is above an overall threshold t. And it's worth noting that there are a couple of different potential scoring functions. For example, using the ratio of known features to total features, or the number of bytes in the message being considered covered by the model M that is chosen with the lowest score. So that basically covers the core of how ZOE operates, how it classifies messages as anomalous. And so now we'll go into the particular data sets that the authors used to validate their tool. They partnered with a large European energy producer, collected approximately 210 gigabytes of data over 6 days from 97,000 devices. There was both a ramp-up period plus like the normal operation of the tool. And for evaluation, the authors used 5 different proprietary protocols, so protocols that they even themselves were not familiar with. 3 of those protocols were operated over TCP, 2 of them were UDP. So the different proprietary protocols that they used covered, were able to validate that the tool works well both on TCP and UDP communication. But for all of the protocols, some of them were text-based, some of them are binary-based, and some of them use both. So the tool is also able to validate that it works well on both text-based and binary-based data. And also they differentiated between incoming and outgoing messages in order to make sure that it's also effective in both of those types of message. So as mentioned earlier, in order to properly validate their tool, the authors knew that they needed examples of malicious messages. So impressively, in order to test their tool, they actually created another tool for the generation of network attacks. In order to do this effectively, they needed to be able to infer protocol rules, meaning that in order to generate an attack message, that attack needed to tailor itself to whichever protocol it was pretending to be. And so the tool built a model of the protocol, similarly to earlier when it built a model of the messages that were coming through, but this time a model of the protocol for the purposes of constructing attacks that adhere to that protocol. And so after doing that, they were able to generate attack messages by randomly choosing an existing message and then using the protocol rule to replace fields that were determined to be variable fields with the attack payload. So now that we've covered both the real data that ZOE was validated over, and also the attack data that the authors generated in order to test the detection of the tool, we can finally get to the evaluation. How well did it do? So the authors used so-called ROC curves to demonstrate the effectiveness of their tool, which plots true positive rates against false positive rates. And these curves are pretty neat. So basically, the curve represents different pairs of, each point on the curve represents a different threshold that was used, and then the corresponding false and true positive rates that came from that threshold being used. So at this point right here, a certain threshold would have been employed, and it would have given a false positive rate here and a true positive rate here. And so with a little bit of thought, you can see how curves like this can sort of help understand how well a detector is capable of, like whether there's a threshold that would give both a high true positive rate and a low false positive rate. So if we had an ROC curve that went straight up, and then straight over, that would be basically would be a detector in which as you raise the threshold, you get more and more true positive rates without getting any false positives at all. And then you hit a certain point, being this corner, where the true positive rate is 100%. So everything that that in this example, for example, that is malicious is being flagged as malicious. And then if you were to continue raising the threshold, then the ROC curve would go along the false positive rate, meaning that you start to get false positives. And so that basically means that there exists some threshold such that you can get 100% true positives and also get 0% false positives. Naturally, in practice, very few binary detectors can reach that ideal, but having a curve that comes up quickly and then over, so comes as close up as possible to the upper left-hand corner, the better the detector. And so one natural way of seeing how good a detector is how much area is under the curve, because for this ideal, we have everything under the curve, so the area under the curve would be 1. But so then like this curve right here has a different area under the curve that is less than 1, but still high. And then another thing worth mentioning is that when you have these ROC curves, when you consider the area that's not under the curve, you can kind of have some area over here that kind of straddles the y-axis, or you can have some area directly above the curve that's sort of like parallel to the x-axis, and those are sort of represent like area over here to the left of the curve represents sort of area where you're getting a lot of false positives before you're getting a high true positive rate, whereas area directly above the curve represents area where the true positive rate isn't able to climb all the way up to the top. So even as you increase the threshold and you're getting more false positives, you're not getting much more true positives. And to try to tie all that together, basically, in this situation, it's important to have very low false positive rates to get, like you want to ramp up the true positive before the false positive gets too high. And so you basically want, it's more important that the curve rises quickly than it is that it gets all the way. You want more area above the curve than to the left of the curve. And so over here in this graph, which shows the area under the curve for different protocols, incoming and outcoming, instead of taking the whole area under the curve, it was sort of benchmarked at a certain spot and then normalized. And so, for example, these dark bars right here represent area under the curve normalized to 0.01. So that basically is only looking at a very small part of the graph all the way over to the left. And so by normalizing it that way, if there is area to the left of the curve, then that would be reflected in the value, the area under the curve that's normalized to 0.01. So even normalized to those like low values, as we can see, ZOE does very well. So the light gray bar sort of represents areas where as the threshold is rising at its lowest position, that we get some false positives before we're getting a lot of true positives. So the two cornerstones of ZOE are its capability to produce these message-specific prototype models and also to denoise. And so the authors conducted experiments investigating how does the tool do whenever prototype models are used but denoising isn't, and also how is it used when only one prototype model is used and denoising is used. So sort of one without the other and vice versa. So this graph right here demonstrates that the denoising is needed and effective. Basically, we have these different graphs for the performance, and when the threshold is low, the performance is low. As the threshold it increases, aka as denoising is employed, we get good performance. And then obviously if the threshold is raised too high, then the performance starts to degrade because we are throwing out relevant features. And then this graph on the right shows the added benefit of being able to use multiple prototype models. So these are ROC curves, keeping in mind that the area under the curve of an ROC model, the more area under the curve, the better. And so this curve represents an instance of ZOE when only one prototype model is used, and the one on top with the higher area under the curve is with 4 prototype models used. So this basically demonstrates that both denoising and using multiple prototype models is necessary in order to get good performance. Here we evaluate ZOE as compared to a tool with similar scope and methodology called Anagram. Anagram is similar to basically ZOE parameterized with 1, 0. So that's basically like a ZOE that does no denoising and only uses one prototype model. And as we just discussed, both using multiple prototype models and denoising are necessary to get good performance. And so it's no surprise that on this ROC model, there's much more area under the curve with ZOE than with Anagram. One of the last experiments that the authors did was to test the effectiveness of their tool against polymorphic blending attacks. So polymorphic blending attacks are designed to take an attack payload and make it look similar to benign traffic. Obviously, this is the exact kind of attack that would be employed against a tool like ZOE. So the authors conducted an experiment in which they generated blending attacks, and they essentially found that the denoising feature that we've discussed provides an effective defense against blending attacks by pruning out the irrelevant features and only considering the relevant ones where the attack payload would result. So now we move on to the related work. So as discussed, ZOE is content-based anomaly detection. Other previous forms of content-based attack detection include trying to reverse engineer protocols to merely detect shell code and network streams, and then obviously Anagram, which was just discussed. But there are other types of anomaly detection other than content-based, such as like network-based. So rather than actually looking at the content of the messages, just looking at different network characteristics to try to detect anomalies. And also, since we are talking about industrial control systems, attack detection by modeling physical processes. So rather than constructing a model of normality for communication, it's constructed for the underlying system. So in conclusion, ZOE is able to challenge the prior held belief that for proprietary protocols, anomaly detection isn't possible using content-based messages, that it's only possible using the network traffic-based or the underlying physical process-based that we just discussed on the related work slide. And so ZOE is able to successfully demonstrate that that content-based anomaly detection is possible. ZOE was able to detect 97.1% of the attacks in the data set with as few as 2 false alarms out of 100,000 messages. And its denoising technique is proved to be effective against polymorphic blending attacks. That concludes the presentation. Please let me know if you have any questions about the paper or about the presentation, and I'll be happy to address them. Thank you.